And Aidan, oh, and Stephen. Oh, great to see you now, Fatma. Good morning, welcome.
Hello,
Good.
sorry I missed the last few.
Aidan, how are you? Nice, Stephen.
Good, how are you?
Good, thanks. We're going to make a start. Eamon is with us as well. He's just gone away to get something, but he'll be back in a sec. But we'll get started. So we're not holding people up. I'm going to put the notes up on the screen. Can you see the notes?
Not yet.
Not yet. Try again. What's happened? Try again. No? Still can't see them?
No.
What am I doing wrong? No, I'll get rid of this. Maybe that'll fix it. How's that? Can you see that?
Yes.
Right, come back to here. Okay, so you've got the notes up on the screen. Psychrometrics, we've talked about heat loads in the previous session. And when you do the camel heat loads, it will produce a psychrometric chart. Sometimes it might tell you that the psychrometrics are not feasible or not practical. Then you need to have a look at your input data, have a look at the psych chart that Camel produces and try and figure out where your problem is. Sometimes it's just the way it's going to be. Particularly with DX equipment, you'll find with chilled water systems and heating water, you don't get that issue so much, but DX can be a little bit tricky with that. But the psych chart's very useful, and we'll go through some of the uses of it this morning. And I recommend that you become familiar with it. Once again, we've only got an hour this morning and we're not going to be able to go through all that much, but just to make you aware of it and let you know that it is very useful, and I think everyone should get to learn how to use it. It involves properties of air at various conditions of temperature and moisture content or relative humidity. When air is cooled, heated, humidified, dehumidified, etc., its temperature and moisture content and other properties change. As I said, it's a very useful tool and enables us to plot processes involved in everything that we do. And cooling, heating, humidifying, dehumidifying are the basic processes, but when you get into more complex projects like laboratories, museums, art galleries, this sort of thing, and data centres, where temperature and humidity tolerances are very tight, sometimes the temperatures are quite low, so they might want 20 degrees. This is when the psychrometric chart becomes invaluable to try and assess how you're going to get the process to work. When I started work back in the old dark ages, we did heat load calculations manually. We didn't have computers. And so the psych chart was invaluable to us. We had to use it. You do your calculations and you use the psych chart to actually calculate the coil capacities and those things, and you can still do that. So just get back to the notes. The chart enables us to determine the properties of mixed air. For example, when return air and outside air are mixed before entering a cooling coil, you can work that out from the psych chart what those conditions are. And that's called the coil entering or enter-on condition. So I'll just throw up the psych chart for a second. So this has got lots of stuff written on it, but what I was talking about then is this is a very simplified cooling process. So I've got return air condition here, which is a point, look, it's at 24 degrees and about 45% RH. I've got an outside air condition of 35 degrees and, well, in this case, 21 degrees wet bulb, which is over here on the saturation line. Mixing those two together, you'll get a point on that line. So somewhere along that line will be the mixed air condition, and you can calculate that. And we'll come to that a bit later. Firstly, I suppose we should just run through what parameters are shown on the psychrometric chart. There's dry bulb temperature, which are vertical lines. I probably should put the chart up so we can just work through it. So along the bottom axis here is the dry bulb temperature with vertical lines going up. The colour charts are handy because it's easier to see different things. Wet bulb temperatures, I'm sure you've all heard of dry bulb and wet bulb temperatures. Wet bulb temperatures are these green lines going obliquely across the chart. Now also obliquely are the enthalpy, kilojoules per kilogram at saturation. And they're also oblique lines. They're not shown on this chart, but they run right across as well. Now, I'll just skip to an aeropsychrometric chart, which is a blank one. So you can see the enthalpy over here, and it's very nearly parallel to the wet bulb line. For all intents and purposes, you can say it's parallel. But if you put a rule between 50 there and 50 over here, you'll find that there's just a slight discrepancy between them being parallel. So also we've got the relative humidity, which are these purple lines, purple curves. Normal room design condition is about 50%, so it would be up on this 50% RH line. At 100% saturation, 100% relative humidity is the saturation line. So that's this curved line at the left side. Over on the right side, in this vertical axis, we've got the moisture content in kilograms of moisture per kilogram of dry air. That's very important for this analysis and for the calculations of latent heat and total heat. So just going back, notice there the difference, kilograms per kilogram on this chart. On the air chart, it gives it in grams per kilogram. So when you come to do calculations, they're normally in grams per kilogram to get all your dimensions correct. Over on the right-hand side here is a sensible heat factor, which is the sensible heat over the total heat. Some of these things mightn't mean much to you at the moment, so just be aware of it. If you're looking at, in a thorough study of psychrometrics, which would take us about at least a few days anyway, it's quite a big subject. You'd find out how you can do all these calculations using the psychrometric chart, and eventually you'll get to the stage where you can do that. So going back to this one, there's also down the bottom here, volume. This is specific volume, cubic meters per kilogram of dry air. So that's saying that as the air temperature changes, the density of the air changes. So normally in your calculations for airflow, you don't worry about it. You can see the values range from 0.8 through to 0.9 here. So as the temperature is changing, your air volume is actually changing as well. So whereas we say litres per second is constant, it actually varies a bit with the density, but we don't usually worry about that. Camel will take that into account when it does the calculations. What else we got? Okay, we'll go back to the notes for a moment. Sorry to be jumping around. When the coil entering and leaving air off conditions have been determined, we can calculate the coil cooling or heating load. And I'll put down here, I've added this note, and I'll send you these notes after the session. In ERA DA09, there is a chapter on psychrometric analysis. This is a very good chapter for you to have a look through because there's a lot more detail in there that I'm going to talk about today. I've actually got it here. So I can, this is DA09, which I keep mentioning, is a really good manual. It's really for doing manual heat load calculations, but it's got a lot of information in there which will help you understand the heat loads. And a lot of this data is used in CAML. So here's the contents: survey and load estimate, design conditions, heat storage, solar heat gain, etc. And there's a chapter on psychrometrics. I'll just have a look at that for a second and just show you that. Applied psychrometrics. So it's worth having a look through this and getting familiar with what you can do with a psychrometric chart. It gives you various types of processes and how to do the calculations. And this will, if you have a look at this, it'll probably give you a better understanding of what CAML is doing. So when you get a CAML result, if you understand the psychrometrics, it makes it a lot easier to understand what's going on. Now, you can see that there's a lot in here, and I can't go through all that now, but have a look at it. And if you can develop a good understanding of that over time, it's not something you need to do right now, but if you can understand that, that will help you a lot with your heat loads. Okay, so we've talked about most of those things that are on the chart. The comfort zone is a range of conditions generally considered to be acceptable for human comfort. So going back to when we talked about design conditions, we talked about the comfort chart last session. The shaded area on the chart, which I'll come back to in a second, shows a typical range from 22 to 27 degrees and 40 to 60% RH. Common internal design conditions are 24 dry bulb, 50% RH, which corresponds to 17 wet bulb and a moisture content of 9.4 grams per kilogram. So let's have a look at the chart again. So that star is the typical design conditions for a cooling process for just an office space, something that's not too sophisticated. 24 degrees, 50% RH, which is the 50% line, and reading across the green line on the wet bulb line, that comes to 17. On the you just take that line across the saturation, that tells you what the wet bulb temperature is. And the moisture content, you'd take a horizontal line across here, and it's about 9.4. Okay. Now the dew point. The dew point is a condition to which air must be cooled to become saturated with water vapour, i.e. 100% RH, assuming constant air pressure and moisture content. At this point, the air cannot absorb any more moisture. At the dew point, the dry bulb temperature equals the wet bulb temperature. So again, looking at the chart, if you take this horizontal line, this horizontal red line here, I've got a tag on there, sensible cooling or heating. We'll come to that in a minute, but at 32 degrees dry bulb and a moisture content of 0.1 or 10 grams per kilogram, take a line straight across there, and the wet bulb temperature is 14 degrees. Sorry, the dew point, which is also the wet bulb temperature. It's the same. Dry bulb and wet bulb temperature are the same at saturation, and that is the dew point for that condition. So sometimes people will ask you, what's the dew point if the air is such and such? And this becomes important because in humid conditions, you get a lot of condensation because the dew point is very high. And if the air comes into contact with a colder surface, moisture will start to form and cause dew. Condensation will occur, causing dew. And this is basically the principle of a cooling coil. So this is what I'm leading to. So that was the example there on the chart. Air at 32 degrees and 10 grams per kilogram, the dew point is 14. And this is how a cooling coil works. The warm and moist air entering the coil comes into contact with the cold coil, and the entering air is cooled and dehumidified. In practice, the coil can't actually cool down to saturation. It's just one of those things that it's physically not possible, but can usually achieve 90 to 95% RH. So when your suppliers give you a coil selection for your project, they'll usually say that the dry bulb is a bit higher than the wet bulb because they can't achieve saturation. And this is due to particles of air bypassing the cold surfaces of the coil due to the physical construction of the coil. So the coil has what's called a bypass factor. And this is another input into CAML. It'll ask you for a bypass factor. And it's basically to do with the construction of the coil. And once again, DA09 will give you a guideline on how to determine the bypass factor of a coil for different situations. Depends on the number of rows, the number of fins in the coil, basically how it's constructed. And if you can imagine, a tiny particle air can pass through the coil without touching anything. It doesn't come into contact with any of the cold surfaces. So that gives you the bypass factor. The closer your fins are together, the closer the coils are, the tighter packed the coil is, your bypass factor will be low. If it's a big open coil, bypass factor will be high. When the coils are installed, the way they're circuited is the coldest part of the coil is on the air leaving side. So as the air enters the coil, it's at the warmest part of the coil, if you like, and it gradually cools down as it passes through the coil and reaches the coldest part as it's leaving. So on the psychrometric chart, what I've shown here is if you're cooling air from this point here, for instance, well, I'll show you on this one. So this is a simple air conditioning process. The return air is mixed with outside air, and this is the air on the coil or the air entering the coil. The initial part of the cooling process, and I'm going along this purple line, the initial part of cooling is basically sensible cooling until it gets to a point where you've reached the dew point and the air is going to, well, you start to get condensation. Moisture is being condensed out of the air, and so that it starts to follow this direction, which is a combination of sensible and latent cooling. Now this is pretty rough. It's really a curve. Some of the coil manufacturers can give you coil curves for different number of rows of coils, and it's a curve. And so it initially goes along cooling sensibly and then curves down with a combination of sensible and latent cooling until it reaches a point where it leaves the coil, which is down here. Now, in this case, this is just a rough thing that I've done. This is saying the air is 80% RH when it leaves the coil. Normally, it's more like probably 90%, so it'll be a bit further out. Okay, now sensible cooling, we've sort of talked about that. It refers to a cooling process that reduces only the dry bulb temperature at constant moisture content. That's represented by the horizontal line of the psychrometric chart. The equation for sensible cooling or heating is this one here, 1.213 times the airflow times the change in temperature. These are very handy calculations, equations for manual calculations and checks, and you'll find that you'll use this again and again. And if you're ventilating a space and you're trying to remove heat from the space, this is the equation you would use, okay, such as a lift motor room or a generator room or something like that, as long as you can determine what your delta T needs to be. So in the Aero handbook, I keep referring to this. This is a really handy thing to have on your computer or even buy the book. There's the sensible heat equation, and that's how they've worked it out. It explains that 1.025 is the specific heat of moist air, 0.845 is the specific volume of moist air at those conditions. You come up with that equation. So that's a really important one to remember, because you'll find that you use it again and again. Latent heat is represented by, we'll just look at the psych chart again. So sensible heat is along that horizontal line there. So it could be cooling or heating. If you're doing a heating process, you're starting from a cold temperature. Let's say it's down here 15 degrees, and it's going to go along this line until it leaves the heating coil at some temperature, whichever you choose, whatever you want to do for your design. But latent heat is a vertical line, so it's at constant dry bulb temperature. Now these are not quite the way it works, but this is just giving you an indication of what it means. Latent heat, if there's no sensible cooling going on, latent cooling will just go down that line, and latent heating will go up that line. Latent heating really refers to humidification. If you're adding steam to the air to increase the humidity, it would go along a vertical line like that at constant temperature. So there's the equation for latent cooling, 2.9 times the airflow times delta W, which is the moisture content. Once again, that equation is there. 2.9 times litre second times grams per kilogram. That's a very useful equation to remember or to know where to find as well. So I've talked about what those processes are. Humidification refers to a process that increases the moisture content at constant dry bulb temperature, represented by a vertical line on the psychrometric chart. Sometimes in a heating system, and particularly down in Melbourne, where you do have a requirement for heating in winter, sometimes the relative humidity can get low because of the heating process. So when you look at the psychrometric chart, again, these are just stylized processes, but if the air is cold, let's say it's 5 degrees and you're heating. So you start over here and you're heating along the constant wet bulb line. You can see that the humidity is getting quite low. If you're getting up to say 20 degrees, if it starts at 5 and you get to 20 degrees, the relative humidity is already down to about 35%. Don't take that as gospel, but this is just an example. That's getting a bit too dry because 40% is probably as low as you want to go with humidity. And I've mentioned here that I don't know whether you've noticed walking around the office sometimes, you touch something metal and you get a shock. You get a static electricity discharge. Has anyone ever experienced that? I'm sure you have. That's because the relative humidity is too low, and it's quite common in heating systems. So what can be done is you can put a humidifier in and just add some moisture to the air, and that'll bring the humidity up. So you'll get a combination of the heating, but also you're moving up this latent heat line. So in effect, you're getting an oblique line, such as this one here, for instance. You're heating, but you're also humidifying. I hope that makes sense. And also, if you're dealing with, particularly in, well, the data center is critical, but even a comms room, if the humidity gets too low, that can cause problems with electronics. And I have experienced this, that generally you're cooling, but if the humidity goes below 40%, sometimes you can get arcing with electronic components, and that's bad because they fail. Excuse me a sec. Now, total cooling is basically the sum of the latent and sensible cooling loads. So the grand total heat is TSH plus TLH. That's common terminology, which you'll probably see in Camel. So you can just add once you've worked out the sensible heat and the latent heat, you can just add those together and you get the total. There's also an equation in the aero manual that you can work it out, but you need to measure the the enthalpy at both points, entering the coil and leaving the coil, and you can calculate the capacity of the coil that way, and you can check it against the sensible heat and latent heat, and they should be the same, give or take, you know, a bit of percentage, because the psychrometric chart is a manual tool. I think you can get an electronic psych chart, but just be careful using that. Okay, so cooling cycle. As I mentioned before, the most common cooling cycle is a simple thing where you've got, say, a DX split system cooling an office or a house. You have a mixture of return air, which is recycled from the space, and outside air entering a cooling coil. So the mixture is called the air on, where it enters the coil, and it leaves the coil at a reduced temperature and moisture content. The leaving air is called the air off, and that's delivered to the space. So if we go back to the psych chart, that's this simplified cooling process. There's a couple of things to be aware of here. I talked about what this was before. You've got return air at this point, outside air at this point. You draw a line between the two, and somewhere along that line is the air on condition. Now you can actually calculate that. So I'll go back to the notes. Well, there's two ways of calculating it. Firstly, Camel, if you're using Camel, it will calculate it for you. So you'll get that straight away. But the psychrometric chart can be used to determine the air on conditions by drawing a line between them, which I've done. And the air on temperature, we use this equation here. And this comes from DA09, the Air Guide. It's the litres a second of return air times the temperature of return air, plus the litres a second of outside air times the temperature of the outside air, divided by the total, the supply air, the litres a second of supply air, and that will give you the temperature. So if you want all the theory behind that, you can go to DA09, but I'm not going to go through it now. But so if we've using that equation, let's say we use the calculation and we find that the air on temperature is 26 degrees. Okay, so we get that point at 26 degrees. And once we know that, we can read off the moisture content, we can read off the relative humidity, we can read off the wet bulb temperature. All that information becomes available just through that simple equation. And even though Camel is available, I think you'll find that once you get used to using a psych chart, that you'll use that equation quite often to find out what your air on conditions are. If you're doing simple calculations, it's very useful. And so from there, what I haven't mentioned is in Camel, it's going to ask you for inputs about things like return air duct gain and supply air duct gain, things like that. So they can all be modelled on the chart. And those gains in the ductwork are sensible gains. So you'll get a little straight bit on your psychrometric chart from one point to the next where you've got a duct gain. I haven't put it on here because it just gets a bit complicated for this initial discussion. But the input to Camel will ask for those things, and you can put a percentage there, or you can. Yeah, I think that's mainly what it is, just a percentage. But I mentioned last time, be careful with the percentages in Camel because keep them fairly lean because you'll end up overestimating the load in the end if you keep putting in large safety factors. So once again, we follow this line, the coil performance line down to the air off point, which we call the air off the coil. And then this blue line is called the coil, the room condition line. Now, Air DA09 again explains this in detail. We used to do all these calculations manually back in the day before computers. So this was second nature to us. But when you do your Camel calcs, you'll get a psychrometric chart and you can look at it and you'll see all the various components of the heat load. So where the air comes off the coil, if you've got an input for supply air duct gain, for instance, that means that as the air is passing through the ductwork towards the room, it's picking up heat. So there'll be a horizontal line shown from the air off the coil to allow for that duct heat gain. And that means then the air entering the room is actually at a different point. And this affects the whole calculation of the psychrometrics. I'm just trying to keep it simple now, just to give you an idea of what these things are. So that's sort of the end of the notes. Any on this part of the session, I've gone through that pretty quickly. Any questions? We'll have some questions now if you've got any, and then we'll just move on to evaporative cooling.
I've got a question. You know, on the
Yeah.
psychrometric chart, you've got the air off coil point. How do you know how far down the 90% RH line that point is?
That's a good question. It involves quite a bit of calculation. Once again, without going into detail, we'll just have a look at the side chart. Maybe, yeah, I'll look at this one. There's probably a bit too much stuff on that one. This is where the sensible heat factor comes into it. Okay, so what Camel does is looks at the heat load and the relationship between sensible and latent heat, or sensible and total heat, and calculates a sensible heat factor. And then there's a pivot point. I'll go to the error chart. I don't know whether, see this pivot point here, this circle? That's called a pivot point. Once you've determined the sensible heat factor, you can draw a line parallel to this sensible heat factor over here through the pivot point, and you'll get a line that goes down and cut the saturation curve. This is the manual method. And then you've got to, oh, look, it gets very complex. There's quite a bit involved, but you'll finish up that room condition line that I showed here, that blue line, that's actually parallel to that first line you draw. And that passes through the room condition. Okay, so that line then determines where that might cut the saturation curve. I mentioned apparatus dew point, but this is, I probably should have actually, but the apparatus dew point is what is determining the slope of that line as well. And that's basically what I've just said, drawing the line from the sensible heat factor through the pivot point. And you can calculate this, and I haven't prepared for that, so I'd have to go back into DA09 myself and have a look, because it gets a bit complex, but it's in DA09 and you can read that and determine how that's worked out manually. Camel does all the equations are in Camel to do those calculations. It calculates the apparatus dew point, and it determines where the apparatus dew point is on the saturation curve, and then works out what the air off condition would be. Not a very good explanation, but it is quite complex, and there's a lot in it. So I just recommend that you have a look at DA09 and get familiar with how those calculations are done. And if you do understand it, it makes it much easier to interpret the Camel results. Probably not much of an answer for you, Stephen, but I just suggest you have a look at DA09 to see how they worked it out. I mean, we could spend another hour talking about that. And I am quite happy to go through that as a separate session if you want to. There's a lot more in it than I've got prepared today. So, are you happy with that answer, or did you want to ask me something else?
No, I think I get it. So basically, it's based on your heat loads. You determine the ratio between the sensible and latent heat, and then you determine the gradient, and then you just follow the gradient from the return, from the room condition, go down the line and see where it intersects with that 90% RH line.
Correct, yeah. And you can have that for the room conditions and for the coil conditions, which is another separate process. Back in the days of manual calculations, this was really important, because once we determine the sensible and latent heat loads, and we can get the sensible heat factor, we would first determine the room sensible heat factor, which was the heat loads just in the room. This is what Camel does to work out the supply air quantity. Then you have to work out, if you say allow the air to come off at 90% RH, then you know what your delta T is going to be between the air leaving the coil and the air temperature in the room. So from there to there. Now that distance gives you a delta T, okay? Let's say it comes off here at 11 degrees, and the room temperature is 24 degrees. Again, I'm going to simplify this because it's a bit more complicated than this, but so you've got the delta T for the sensible heat in the room. And the equation for sensible heat is 1.2 times delta T times litres per second, as I said before. So from that difference there, and you know what the room sensible heat is, okay? You've calculated that based on all the loads that are entering that space. So it's the solar loads, the transmission loads, the internal loads. You work out the room sensible heat. You know where the delta T is going to be because you've worked it out from drawing this condition line. Therefore, you can calculate what the airflow is, because the airflow is the room sensible heat divided by 1.2 divided by delta T. However, you also need to consider if you've got supply air duct gain and other things adding heat to the supply air before it actually gets to the room, then you need to modify your chart. So if your air comes off here at 80%, you might have a horizontal line here to pick up the heat from supply air duct gain. There might be heat in the ceiling space that's getting in there from other sources. So you need to take that into account. But once you've determined the actual air off condition, this is why I've tried to simplify it, you can calculate the airflow required to achieve those conditions from the room sensible heat, and using the sensible heat factor. So I don't know whether that's confused it further, but that's how it works. Look, I find it very interesting. I know it's a bit hard to talk about in a very short time because it's quite complex. But if you have a look through D009, just read through that chapter. It tells you everything you need to know, and it's very beneficial. I really recommend that you do that. All right, let's move on to evaporative cooling. I put this in because it's a process that we do use occasionally, and it's probably more relevant to industrial projects rather than the commercial office buildings. Sometimes it's used for make-up air for kitchen systems, kitchen exhaust systems. So you can use an evaporative cooler to supply air for the makeup for a kitchen hood, so you get some cooling. Well, just the opening statement here: dry air flowing over water will absorb moisture and lower its dry bulb temperature while increasing its moisture content. There was a typo there. I had constant moisture content or relative humidity. On the psych chart, what this looks like is I've got two lines along the wet bulb line here. There's a blue one and a brown one. Looking at the blue one to start off with, evaporative cooling is a nice enthalpic process, so constant enthalpy. But enthalpy and wet bulb lines are, for all intents and purposes, parallel. Okay, so if you've got a point on the side chart, here I've got 35 degrees dry bulb, and the moisture content, well, it's a wet bulb of 21 degrees. So that's, say, Melbourne conditions, Melbourne design conditions. So you've actually got some capacity for evaporative cooling in Melbourne in those conditions. And so the process occurs along this wet bulb line. And typically, an evaporative cooler, the best you'll get is about 80% saturation. You won't be able to go to 100% saturation. So if the conditions are hot and dry, you can see that you can go from 35 to 25 degrees. And that's a fact. It works. And in houses, you might, if any of you have got an evaporative cooler at home, some Melbourne houses have them. On very hot days, they work well. You know, it can be 35, even 40 degrees outside, and you come inside and it's beautiful, 25 degrees. But it does increase the humidity. So you need to be aware of that as well. And you have a lot of supply air with evaporative coolers, and you need to have relief. Otherwise, if you close the place up, you're going to restrict the airflow for a start, and the humidity will build up. So you've got to allow the air to escape and have it constantly flowing through your house or the space. This underline, the brown one here, I've just put this here because this is where I live. I live in Mildura, and up here it gets extremely hot in summertime. And we've had days of 42, 43 during the summer, but it's not unusual to get a day of 40 and about 20% or even lower relative humidity. So if you walk around Mildura or anywhere out in this drier country, you'll see evaporative coolers on nearly every roof of a house, because here's the potential for cooling. If you go to 80%, on a 40-degree day, you can cool the air down to 25, 26 degrees. So if you walk into a house from outside and it's 40 degrees, it's 26 inside. It's great. It's really cool. But it has a high humidity and you need to get that air out. So I'll just put that in for interest. So I've got some pictures of, here's an evaporative cooler sitting on a roof. This is more of a commercial style. So in factories, they quite often use it for cooling the factory space, because all you have is a set of filter pads, a fan, and a pump. And these filter pads here are kept wet. There's a fan in behind there. And there's a filter pad on the other side. So the air's coming in from two directions, goes through the fan and gets blown down through ductwork. In this case, it's going through the roof. That's all there is to it. There's no refrigeration. It's just water. You can see here there's a water pipe coming in. That's constantly supplying the water to a little reservoir to keep the water level up. And there's a drain there as well. When you turn the unit off, they have an automatic dump drain. So when you switch it off, the valve opens and the water drains out. So the next day you start with a fresh water supply. You don't want water hanging around because it may get contaminated. So you just dump it at the end of each cycle. There's another picture of a more domestic style. That shows you the fan there. These are the intakes on the side with the filters that are kept wet, and there'd be one on the other side as well. And there's a forward curve fan, which in this case blows out the front. I think I've probably mentioned most of that there. I think I've probably covered those notes. Any questions on evaporative cooling? Yeah. Look, it's not something you use very often, but something to keep in mind. And you might get a job where you do a big house in a dry area, and they're asking you to provide air conditioning options. And depending on how much they want to spend, evaporative cooling is probably worth considering, or at least put it forward as an option. Because compared with a DX system, split systems or VRF, evaporative cooling will be much cheaper, and there's really very low running costs because all you're doing is running a fan. You're not running refrigeration. But I'm not here to sell evaporative cooling by any means. But I just wanted to let you know how that works, because it will come up from time to time, and it is an option for kitchen makeup. But it's important to know that what that process is, and obviously in a humid environment it doesn't work very well, because if you've got an ambient condition of say 37, I know Cairns is about 37 and sometimes 70% RH, way up here, so you can see there evaporative cooling, it's already 70% RH, you're not going to achieve much, so you need to use refrigeration, but in dry climates it can be useful. So we've finished a bit early. I wasn't sure how much time this would take with questions. Are there any other questions? And again, look, I know I've rushed through this. It's a very big topic. I think the main thing is to be aware of the psych chart. Have a look at DA09 and read a bit more on that. We will be doing a more detailed session later on, but not in this program. But as we go through, we'll just keep stepping up to a higher level, and we'll spend more time on these sort of things. At the moment, this is just about awareness and basically leaving it up to you to do a bit more reading. You know, I can't cover everything in 1 hour. There is a lot to learn, but it's worthwhile, and you'll find this, you know, it'll serve you well if you understand the psychrometric chart. Any other questions?
No,
All good?
all good.
Okay. All right. Well, we'll finish there, and I'll send you out these notes, which I'll put a few extra comments on, which might be helpful for you. And on probably on Thursday, I'll send you some notes for the next session and an invitation for that session as well.
Good. Thanks,
Okay.
Peter.
Thank you.
Thank you. Bye.
Thanks.
Yeah, thanks.
Bye.
See
See
you.
you next time.